Hello everyone, today we are going to discuss 3-4 questions related to the topic Newtonian flow, viscosity and cell energy balance for composite cylindrical pipe. So let's discuss first question. In first question we are going to discuss the flow behavior in a stirred tank. The main objective of a problem is to predict the flow behavior in a large unbaffled oil tank using a smaller geometrical similar model, and the goal is to determine the mm, necessary condition for a model to accurately represent the prototype. So for unbaffled stirred tank, the flow behavior depends on impeller speed, density, viscosity, gravity, liquid height, tank diameter and impeller diameter. So let's consider tank radius is capital R, center impeller diameter is capital D, and over here we already mentioned the notations. So at time t equal to 0, we'll speak about at time t equal to 0, system is at stationary and it contains the liquid to height h above the tank bottom. But immediately after t equal to 0, the impeller rotates at a constant speed n and the atmospheric drag neglected, and the impeller shape and initial position are described by the function. S impeller is a function of r, theta and z equal to 0. So as we can see over here, boundary condition. First boundary condition is at the bottom of the tank that velocity equal to 0 at z equal to 0, and boundary condition 2 at the tank wall that velocity is equal to 0 at r equal to capital R, and at the boundary condition 3 at the impeller surface no slip condition where fluid velocity equals the impeller surface velocity. As we'll speak about the boundary condition 4, gas liquid interface, no mass flow through the interface, like n dot v is equal to 0. And similarly, for force balance where viscous gas contribution is there, np plus n dot t equal to np atm. These are the some boundary conditions. Let's see the dimensional analysis and similar to maintain dynamics similarity in the two systems. So for geometrically similar, we can see the polar coordinates are equal to r upon d and z equal to z upon d. Here we need to maintain the dynamic similarity to operate at the same values. As after dimensionalizing this, we'll get these equations for boundary conditions will become like this. After that, we'll get the velocity and pressure profile in the form of this, like velocity should be in the function of r, theta, z, t, the ratio of impeller radius and impeller diameter, tank radius and impeller diameter, and the height of the tank and the diameter, Reynolds number and Froude number. And similarly for the pressure profile, and for a given impeller shape and location, the locus of the free surface is given by this following equation. So the result provides the necessary condition for the proposed model experiment. Two systems must be geometrically similar. They operate at the same values of the Reynolds number and Froude number. As the conditions are, we can see over here, equation 3.7 and 3.7, like 3.742 and 3.743. And this is important reason, namely that the smaller tank too fluid of smaller kinematic viscosity to maintain dynamic similarity. And as we can see that this problem showed that the flow in a stir tank can be predicted using smaller model by maintaining Reynolds number, Probe number and geometrical similarity. This ensures similar velocity, pressure and flow pattern. This dimensional analysis helps in accurate and economical prediction of real system using model. So let's just discuss second problem. Here we need to develop the overall heat transfer coefficient for the composite cylindrical pipe wall. As shown figure over here, there are three reasons. Mm, like we can see reason 1, 2 and reason 2, 3. So hot fluid outside, temperature TB, and the cold fluid flows inside, that temperature TA. It flows readily inward, outward through layers. And as we discussed that there are two reasons. So derivation uses three fundamental laws like shell energy balance, Fourier's law and Newton's law. Okay, so first the energy balance we did over here. uh, QR heat at R 2 pi RL minus QR heat flows outside of the shell at R plus delta R into the 2 pi bracket R plus delta R into L equal to 0, which can also be written as that following equation. Dividing by 2 pi R delta R will get, and the delta R tends to 0, we'll get the reason 1 equation like d RQR upon my dr equal to 0, and integration of this equation will give us RQR equal to R naught Q naught. So for reason 1, 2 and reason 2, 3 will get this equation, and after calculating and rearranging this equation we are going to get at surface 0 we'll get T a minus T naught equal to Q naught upon my H naught by using the Newton's law of cooling, and at the surface 3 similarly we'll get T3 minus Tb equal to Q3 upon my H3 equal to Q naught upon my H3 into R naught upon my R3, and the addition of all these 4 equations, Newton's law of cooling, Fourier's law and energy balance, will finally get the heat transfer coefficient, overall heat transfer coefficient over here 1 upon my R naught upon my U naught. So this problem derives the overall heat transfer coefficient U naught calculated by combining convection and conduction resistance across all n layers for composite cylindrical wall by applying energy balance, Fourier's law and convention boundary condition that we already spoke about. It shows that heat transfer through the systems occur by convection at inner and outer surface, conduction through multiple cylindrical layers. All these resistance combine to give the total resistance. The overall heat transfer coefficient is obtained as the sum of the normal resistance in a series. So let's speak about the third problem, mass transfer in industrial observer. Here the gas bubble A rises through liquid B column, and the bubble range diameter is 0.2 to 0.6 centimeter, and the velocity is 15 to 35 centimeter per second. So we just need to prove that a range of average liquid side mass transfer coefficient value lies between 0.018 and 0.047 centimeter per second. As the all parameters are given, we just need to calculate each and everything. So as you know, we have gas bubble, and here we can apply like penetration theory. Liquid near the bubble is not stagnant. Instead of liquid element touch the bubble surface, stay for a short time, move away and are replaced. So diffusions happen for a limited time only, not forever. Not forever. And that time is called the exposure time. So bubbles rise with the velocity UV. A liquid element stays near bubble roughly over distance and bubble diameter is dp. So as we can see, T exposure is nothing but distance upon the velocity and dB upon the UV. So for average liquid side mass transfer coefficient, we can see the formula is KL equal to under root 4 dAB upon my pi T exposure. And as we know, the formula of T exposure is dB upon my UV. After putting the exposure time in the mass transfer coefficient, we can get this equation like, and from the formula we can say that if the DAB is increased, then KL will also increase. It's because faster diffusion will be there, and as UP increases, KL increase and less contact time and stronger gradient will be the reason over here. And as dB increases, KL is decreases because dB is in the denominator in the formula as we can see over here. So longer exposure and weaker gradient will be there, as DAB value will be given 1 into 10 to the power minus 5 centimeter square per second, and dB it is range from 0.2 to 0.6 centimeter, and UB is 15 to 35 centimeter per second. So KL value is there, the formula is given over here. And to find the minimum Kc, we need to choose the condition that make KL smallest. So velocity should be low. So we are choosing 15 centimeter per second, and diameter should be large, as KL will be increased if diameter will be large. So we are no, sorry, KL will be increased if diameter will be small. So here we are choosing 0.6 centimeter, and after calculating we will get 0.018 centimeter per second. Similarly, for find maximum Kc, we need to choose the high velocity like 35 centimeter per second and smaller diameter 0.2 centimeter. After putting the values, we will get 0.047 centimeter per second. We'll find the liquid side mass transfer coefficient is less than 0.047 centimeter second and greater than 0.018 centimeter second. Hence we proved that the range of average liquid side mass transfer coefficient value lies between 0.018 and 0.047 centimeter per second. So let's now discuss the last question. Flow past a circular cylinder. To study the pressure and flow pattern past a cylinder while minimizing experiments, dimensional analysis is used. So we need to determine flow pattern, pressure distribution, and conditions to organize experiments so that minimum number of experiments is required. So for idealizing physical setup, cylinder diameter of a cylinder is capital D, and where fluid is incompressible, constant density and viscosity. As we know, initially fluid at rest and cylinder also be at rest. So initial condition as given over here, that x square plus y square is greater than 1 by 4 d square, or here is greater than 1 by 12, and velocity is delta x v infinity. So these are the boundary condition 1, boundary condition 2 and boundary condition 3. So using the equation of change, we are going to get this boundary conditions And by solving equation of change, we got the final equation for velocity profile and the pressure profile like this, that velocity is the function of x, y, z, t, Reynolds number, and L by D ratio, and pressure similarly for pressure. So from here we are getting this, that we no need to vary the diameter, velocity and density and viscosity separately. Just we need to vary the Reynolds number and the ratio of L by D. So as you can see the flow behavior at the different Reynolds number. So let's discuss one by one. Effects of Reynolds number on flow. The flow pattern changes strongly with Reynolds number. As you can see in the figure, that if Reynolds number is very small, like 10 to the power minus 2, then flow is completely smooth and steady. Fluid moves symmetrically around the cylinder, and we are not saving the separation of flow. So over here viscous is dominating. So let's speak out the second one, moderate Reynolds numbers, like Reynolds number is 10 over here. So here flow is still mostly orally, like in symmetric pattern only. A pair of vertices appear behind the cylinder, as you can see in the figure. These vertices are symmetric and steady, and flow start to separate behind the cylinder. At higher Reynolds number equal to 100, here we can see the unsteady flow. One common vertices straight forms as a vertices shade alternately. So here large Reynolds number is 10 to the power 4. Here transitions to turbulence, the wake becomes irregular and disordered. So the flow is disordered and fluctuating. This transitions to turbulence, as we can see in the figure. So thank you.